So this is going to be an update video to VORs and SDRs series. It's been a while since I did an update, and a fair amount has happened since then. It's been a pretty difficult January, so I had to go visit a friend at in the hospital in Seattle a couple of weeks ago, and it turned out the most practical way to do that, and we actually ended up making it somewhat affordable, was to charter a plane to fly us up there. So the benefit of chartering a plane is that it doesn't have the same rules as an airliner, and if you work it out, you can use radios, and this is something that is pretty strictly forbidden with airline travel. So I was able to bring two RTL-SDR receivers, a power splitter, and an antenna, and capture a few VORs while we were traveling. So the path we took from Corvallis to Boeing Field was pretty straightforward. We started at the Corvallis airport, and we had to do instrument flight rules. So we did the standard instrument departure out of Corvallis, which is to turn and then head out towards the east. And then we picked up air traffic control on the radar, so that's why the track begins here. This is the first point that FlightAware had our radar, and we were in the system. So by the way, these pins are VORs. So there's the Corvallis VOR, there's the Newburgh VOR, Eugene, Newport, etc. So our flight path was to cross directly over the Newburgh VOR, then to cross the Olympia VOR and change direction slightly. And then at this point, we were in Seattle's Class Bravo airspace, so they were vectoring us around for instrument approach at Boeing Field. So it's a pretty straightforward path. It's interesting in that we passed directly over two VORs, and I have a really great track that I recorded from the Olympia VOR. For some reason I didn't get the Newburgh. I've got a little bit of Astoria, a little bit of Battleground, and a little bit of Seattle Tacoma, which is down there, in Seattle Tacoma. Okay, so I kept track of each of the files that I recorded into and their start time as recorded by the operating system. So you have the bytes of the file divided by the sample rate multiplied by the number of channels, so we have in phase and quadrature, and then multiplied by the size of the basic unit. GNU Radio records things as 32-bit floats, so it's 4 bytes. So by dividing the bytes by this quantity, we have the number of seconds that was recorded in each of the files. So that's these durations that we get. In addition, we will know how many seconds to pad before each of the files, and then how much padding will be required at the end of each file to make it so that they're all the same length and their start times are correct. Here I just have the latitude and longitude of the VORs themselves, their elevation above the ground, and the magnetic variation that they're set to. VORs are set to magnetic north, and they're in different places, so the variation is different. Also, magnetic north changes relative to true north, and so usually they'll also have a column that is the year that the variation was set to true north. Okay, anyways, so I use these durations and Audacity to line up the files. So what I did is I just went through each of these files, each of the reduced files, and I made processed WAV files. And I just use WAV files because it's really convenient to use Audacity. So the WAV files have two channels. The top channel here is the signal strength, and the bottom channel is the radial that I'm at. So this bottom, the Newberg VOR is actually only going away from it. So I didn't actually have a chance to start recording before we crossed it. So 0 on the phase line is true north, and -1 and 1 are both equal to, magnetic north. -1 and 1 are magnetic south, and then in between, negative numbers and positive numbers are east and west, and I don't remember which is which, but we can tell here in a second. So we're flying magnetically almost due north away from Newberg. So the battleground VOR is not reliable. It doesn't make sense why we're going due south of it. There's actually two signals in that battleground capture, and I wasn't sure which one was the true battleground VOR in post-processing, so I don't actually trust this trace. So I thought we could hide it, but whatever. Okay, the Astoria VOR is somewhat more interesting. Even though it's really far away, you can see it's quite far from our path, and I was only able to actually get a signal from it way out here. So we're to the east of the Astoria VOR, and you can see that we're in positive numbers, and that they are slowly changing. They're slowly becoming more north. So that goes along with the idea that we are traveling tangentially along it. If we were to follow this line outward, it would go up to being, south. And then if we kept following it this way, it would be north, and it would never go to this side. Okay, so the Olympia VOR is my favorite by far. It's there's two things about it that are really cool. One is you can see that we have the signal strength getting better and better and better. We can see the threshold where the signal becomes reliable here, and then it clips off the top over here. So these would get, these would be much higher. And then you can see when we travel directly above it, the signal strength drops way down, and then has a little tiny peak, and then picks right back up on the other side. And that is really fascinating. I kind of knew that would happen, but I didn't think it would look so cool and so clear. Also, you can see there's a great deal of ambiguity as we pass directly over the station. As we're headed towards it, we're almost due south, and then we cross it, and then you can see that we're traveling east of north, directly away from it, because it's basically a straight line. And then Seattle is like Astoria in the sense that we're traveling tangentially from it. So if we scroll up, we can see that the Seattle station is here, and we're kind of going along it. And so we can see that we start fairly south, and then we get closer to being north when the signal cuts out. And I turned all this stuff off because it was getting time to land, and I was putting everything away. Okay, so to explain a little bit about this application, it's a program that I wrote over the last week, and my goal with this is to have a VOR simulator. So I loaded in our track, and what it will do is I'm going to have it export virtual baseband signals for each of these VORs given a fake track, or in this case a real track. and then we can use the output of the VOR simulator on another program, which is the synthesis program. So I'm going to use the ground truth data that I collected, compare it to the VOR simulator results for the exact same path, and see if how good a fidelity I can get out of the VOR simulator to match real-world data. And then later on, I can use that simulated data, like sort of best case, perfect data, to build the app that goes from VOR data into navigation data. So I'm going to be open sourcing the VOR simulator. It's got a lot of really convenient code in it if you're into navigation and stuff like that. To me, the sort of the coolest code is what I've gotten from a website called Aviation Formula, which is nothing more than an enormous list of really great navigation formula, including distance between points, latitude and longitude given radial and distance, which is a big one. But the two most exciting thing is intersection of two radials. So we can get the latitude, longitude of an intersection formed by a true bearing from point 1 and a true bearing from point 2. And that is perfect. Exactly what we want to find out the latitude and longitude from two VORs. Okay, so yeah, so I've implemented quite a few of those functions, not quite all of them yet, and I'm using Swift, so sorry it's not going to work on anything but a Mac, but I'm using it as an excuse to learn Swift anyway, so if you don't like it, sorry. One cool thing that I'm able to do with it, though, is we're able to use location and vector types. We're able to make types out of them. And then we can do really convenient operator overloading to do math on these types. So, you know, we've got adding a location and a vector gives us a new location, which would be if we started at the location and went in the direction of a vector. We can accumulate vectors. We can get the distance between 2 points. We can get the course between 2 locations. And I've also got a pretty comprehensive set of unit tests that will verify that those functions act according to how we expect them to. Also, I've been using it as an opportunity to learn how to do MapKit. So all of that MapKit stuff was fun to write, and the simulator just does, you know, really neat stuff. Like I can go and import a KML file from FlightAware, and it will load up the track, draw it, zoom in, load all the nearby VORs, and drop pins. And that is just really cool. And that only took, you know, 200 lines of code. Okay, so I think that's it for this update. Sorry if it was a bit long in coming and a bit rambly. I'm in a weird spot in the project where I don't have a lot of clear milestones that I've achieved, but I've done a lot of work, and I'm getting cool results that are just hard to explain. So yeah, so that's it for this update. Sorry for missing Saturdays, and if you like it, make sure to thumbs up, share, and subscribe. Thanks again.